Okay, we've got 8 o'clock. Well, let's get started. Good morning, Stats.
Good morning.
Welcome to our Thursday session. Thank you for all being here and on time. That's really terrific. We like to see people developing these good habits early in their lives. And it's a great habit to have to go and be punctual, but to be able to be punctual early in the morning is actually a life skill and something that we very much appreciate in the professional life. So good of you to be developing that. I'd like to spend just a moment to tell us about where we're going for the next week or so. As we're coming up on some new events for us, we haven't yet had our first exams, and we'll have those toward the end of next week. So you can see that we're coming up on this exam 1. And the exam can be a little bit different this year than I've had them in other years. What I'd like to do is, probably tomorrow, I will hand you a writing prompt. Our exams are going to take the form of written exams, where you're going to take this information home and actually generate prose. You can generate essays that might be something like 1,000 words or 1,500 words, so only a few pages of writing. And you'll have a whole week to do this. And when you come in on exam day, your exam basically is written. I'll ask you to submit an electronic version. You'll also have paper versions. And we'll do something like a writing routine, a writing workshop. We will see each other's writing on this. And the idea will be that the questions will have you integrate some of the ideas that you've learned, some of the concepts that you've learned so far in this semester, with things you've learned from classes, or maybe with an article or two that'll have you reading that will have something about psychological science and maybe some of the topics that we've been covering so far. So let's do some complex integration of information, but we won't have any particular time pressure except for the fact that we have 1 week to do this. This is very different from the way I've historically run my section exams, where you come in, you have 15 minutes to answer a bunch of short answer questions. And I think I'd like to try to do some kind of formats. That's what we're going to be next Friday. It'll be a take-home exam in the form of a written essay, and we use that Friday as something like a writing workshop. We want you to be able to compute well, but also to write well, and also to speak well. So we had a great example of that on Monday when Melanie gave her talk, and we had Sarah giving on Monday. So chances to speak, chances to write, and virtual writing, and lots of chances to compute. On the chances to compute, that was Friday, so I'll work backwards in time toward today. Okay? And next Thursday we'll have our first computer quiz. And today we're going to be spending much more time on the computer, just doing exercises, some of which we've done before, but most of which will be brand new. And then maybe tomorrow we'll do some more of those. We'll have all day Wednesday to be working on that, set us up for the computer quiz on Thursday. Any one of these quizzes is not worth a really large amount of points. So I think it's important that we distribute our practice and also distribute the points so we don't make anything too high stakes. So we just get there more along the lines of a ramp rather than these huge steps. So that's going to be for next Thursday. So Friday is the take-home exam will be due, which you have a whole week to work on that computer quiz on Thursday. That will be right. And I think we'll finish pretty comfortably in 15 days. Okay. So Wednesday, we'll be setting you up even further for the computer quiz. We will spend some time with some computations on chi-squares, and we'll introduce chi-square tomorrow. I know that you've had that before, but we'll have our review of that tomorrow. We already have 10 ed available, so there are now 15 10 ed questions available to you for tomorrow's session, and those are all on chi-square. And some of that material can be entered by your chapter 13. You can also use cookies or other sources that you have. I do have a chi-square video for my research methods class, and that chi-square video is available to you. Use whatever you need to answer the chi-square questions. All right, and then on Monday, we'll call that chi-square Cosmo Monday. Again, we'll be reading about film Cosmo and African Great Parent, as I mentioned earlier. We'll do that for 30 minutes, and then we'll have Sarah make a presentation for 15, and we'll have 5 minutes of questions. So I think that takes us through the next 8 days of classes. Who's okay with that? I'll give you other reminders about what will be on the quiz as we get a little closer, but we'll develop those skills on Thursday. Okay, so having done all of that, why don't we now move into where we left off yesterday? And I wonder if you can join me out on the S drive when we go to the standard deviation set. So we can call that up. We go out to my computer, the shared drive, and then after the shared drive, zoom into Matthews and PSYC 370, the resources folder. There's some practice sets there, and we were computing in Excel because we realized that not everybody here has used Excel before. Some people were really quite comfortable with this. Okay. So when you get out that far, I wonder if you can raise your hand so I can see who's got it. All 10 of us have that. Is that real? Yeah. Okay, really good. Okay, so all we're doing here is learning some Excel commands. We learn the average command, which some of you already do, and we learned something about spatial relationships when we coded this very first set of deviations. I wonder if somebody can remind us what it is we said about spatial relationships when we tried to code that very first deviance. Do you remember what we learned about that? We said that that particular score was equal to the neighbor to the left minus this cell, which is something like 20 cells down. So go over 1, go down 20, and find the difference of those two cells. I'll do that again. I'll generate an error. Okay, so I'm going to say, I want my deviation score, which is score minus mean. Here's my score. I'll subtract from it the mean. Okay? And that works. I get that 1.55, then I'll drag this down. Do I have a list of deviation scores? Yeah, and why not? Thanks.
Because when you break it down, each row also went down.
Okay.
One.
And that's good for the first part of this because I said go over to my left and then down by 20. And over here I said go over to my left, so far so good, and then down say 20. And that put me here. Okay. So we made this one we call the noting that what we're really doing here is a spatial relationship. Go over so far, down so far. And we needed to fix that by putting in these frozen bits. And the way that we freeze things is by entering $. You can freeze a particular column, you can freeze a particular row, you can freeze both a column and a row, and you want to reverse the sum of both of these. Okay, really. So now we've got the deviation scores. Anybody want to hazard a guess? If I were to sum up the deviation scores, what might they add to it? Okay, does anybody know how to take a sum? Why don't we find out? Anybody know the command for taking a sum? Yeah, it's equals, so we always put in the equals, sum, okay? And we open a left parenthesis. And that means we can now cursor to our heart's desire, and we can go like this, that, and I'll let you enter. But here's the code, just in case everybody uses the sum. That's the syntax. Okay? So we've learned the average command, the sum command, and does anybody tell me what we're getting at? That might be intuitive to some people, but that's not intuitive. What is that telling me? People are not sure of this. All right, anybody have an idea about what that's saying?
I think it's saying that the answer is negative 3.55 times 10 would be 15.
Yeah, right. Okay, so essentially, we're at 0. This is essentially 0. So we have a bunch of scores. We took any given score's deviation from the mean, and then we sum the deviance, and the deviance added up to essentially 0. It's actually giving us 15 digits of precision. And so we got to pretty close to 0. Can somebody give us an intuition about that? Why would that be the case? Why would we have a sum that gets close to 0? It isn't always close to 0. Just to show you that it isn't always close to 0. And you might think, well, that's something about the sum command. I say equals sum, and I will take a sum of my scores. And my scores sum to 101. So it's not like there's some property of the sum command that intrinsically gives us 0. That we call this the 0th moment, like the mass or the sum or something. Like the sum goes to scores. So we have 109 as the sum, but when we sum up the deviates, they add up to 0. Let's take a look at the deviates. And notice that all the scores are positive. about the deviates? The deviations. They're not all the same sign. How would that be? What differences?
Naturally, you're gonna have scores that are low.
That's the thing. The point about them, it's marking something toward the center of that distribution of scores. Some are going to be on this side, some are going to be on that side. If you take the negatives and the positives and you combine them, it should come out to something like zero. Right? You can think of a mean as a balancing point. Right? So some of the scores are on this side, some on that side, combine them, it should add up to zero. So this is kind of interesting. Okay? We have now, we're trying to get to the standard deviation. Now, I'm sure that many of you know how to compute standard deviation using that Excel command. We're trying to develop it manually, and we have a bit of a problem. Once we get the deviation scores, they sum up to zero. So how do we begin to quantify those? The answer is actually quite interesting. We've, as a field, in fact, all scientists have adopted a particular kind of measure of dispersion called the standard deviation. But what you could do is you could simply take the absolute value of each of these and sum those up. And that would give you some indication of how much dispersion you have. Does that work for you? People see that you could have done it that way. But what did we actually do? Maybe you know the next step in our computation. Does anybody know the next step? Okay, we need to square them. Somebody said that. So I'm going to go over here to column E, and I'm going to call this, as an abbreviation, something like square deviation. I'll make that red, but you don't have to. And that would be something akin to this. We can say that we would have still S minus n. Okay? But now we're going to square that particular difference. Okay? So we're going to take the difference first, remembering PEMDAS, right, our order of operations. And does anybody have a handy mnemonic for this? PEMDAS, this is the order of operations. So it's, you tell me. What is it? It's from this. Yeah, and please excuse my dearest Sally, because it's one of those about that. Okay? So we now need to first take a different square, so we won't put those in parentheses, or as we're showing here. And then we have to exponentiate it. We have to simply square something. Does anybody know what symbol we use inside of Excel to square something? This is actually true generally in computers, not just Excel. Okay? And we do this every year with all of my psych 200 students and 77 students. We have to go like this, so you know what I mean? And this is our carrot. Okay? And where do we find our carrot? We're finding our carrot over the 6. So what we're going to do is the score minus mean is a quantity, and then we have to now exponentiate. We raise that to a power, we're only going to raise it to the second power. Okay? So we've already put the score minus mean quantity here. So now what I want to do is I want to say this cell is equal to my neighbor to the left, and I want to raise that to the second power. Okay, and now I have a squared square. And I'll center that. So neighbor to the left, squared, and then remember our trick, I can grab that on the right hand knob, and I can drag that down. And now that get another column down. When I have a column squared, that gets us around the problem of having multiples and units. This is the convention that we've adopted. All right, and what we say is equal sum again. And now we take the sum of the squared units, and we get the sum of squares. Who remembers hearing about that? Sum of squares. So what that is the sum of these squared units. One of the ways of thinking about that. By the way, another way of doing this, every once in a while, you get a little menu items. These tend to come together across different versions of Excel. But what you do is you click on that summation sign in your upper left right-hand corner, point it to it up here, and I think that will work for us. It usually figures out how high you want to go, and it basically gives you the sum of everything. So we have the raw scores, and then we have the deviate, which should add up to 0. That makes sense. We have some of the square deviates, we'll call this SS. Okay. All right, so anybody know the next step that we might use if we wanted to make our way toward manually computing the standard deviation? We have the mean. You probably know an Excel command for the standard deviation, but what might we do with the simple squares in order to get to the standard deviation?
dividing by the number of respondents.
Okay, divided by the number of scores that we have. And you know what we call that? So that's exactly right. That's the next step. We have a total sum of squares. We can divide by the number that we have. You know what that quantity is called? So you know what that quantity is? So this is going to be SS divided by the number. You know what that thing is? It's called the variance. The variance is simply defined as the sum of squares divided by, actually there are two flavors of variance. There's population variance. Let's pretend that we had a population on a very small island that had exactly 20 people. That would be the entire population. So the population variance is defined as SS over N. And then we have a sample variance. We might pretend that these 20 people are 20 out of something like the 2,200 or so that we have on campus. So similar kind of definition, but not exactly the same. Anybody know what the sample variance is? It's still SS, I'll give you that much. Divided by simple units. N minus 1. We'll come back to that and see if minus 1 minus this. Why don't we see if we can get something like a population variance? I'll call this population variance over here. And so Hannah was correct. We're going to say equals my neighbor to the left divided by, and what's our N? What do we have? 20? Okay. And I wind up with a population variance of 3.5475. What do you confirm that number? Can I use anybody here? Just take our neighbor to the left and divide it by 20. And then we can also get our sample. And that's going to be equal to, one more time, the sum of squares divided by, we can do this a couple of ways. We could say 19 because that's 20 minus 1. Or I'm going to do it parenthetically. I'm going to spell out the whole thing, 20 minus 1, so that it becomes very obvious where that 19 came from. And we get a slightly different. It should be bigger because we're dividing by a slightly smaller number. So hopefully that works. So now we have the raw scores. We have their deviations from the mean. We have their square deviations. We have the sum of their square deviations. Then we get this statistical quantity called the variance, and that comes in two flavors, one for the population, one for the sample. By the way, this is the accepted definition of sample variance. Does anybody know why we would subtract 1 from the denominator and use n minus 1 rather than 1? So is it clear that by dividing by n minus 1, you're going to wind up with a slightly larger quantity over here? Is that okay, so the reason why you want to have a slightly larger quantity conceptually is this would be a good item for maybe the final instance. The notion is if this were a sample, probably you don't have the most extreme scores from your population in your sample. You could. Let's say that these are depression scores, and we're getting depression scores from a sample of depressed patients. It could be that in the entire population of depressed patients, there's somebody who has the most extreme score. That person could be in your sample, but probably is not in your sample. You've got thousands of people, and you've got in your population, you have a sample of 20, you probably didn't get the tallest. You probably didn't get the most depressed. You probably didn't get the wealthiest. You probably got something that is slightly less extreme than the most extreme score. And for that reason, because the most extreme score in your population is not actually in your sample, you might want to take some kind of compensatory measure. You might want to say, how can we possibly maybe begin to estimate or recover in some way that more extreme score? So what the field of science generally has adopted is, why don't we just divide by n minus 1? And see if that gets us a slightly broader deviation that is more likely to be representative of the actual population. Who's following that? Kind of subtle logic. And then what statisticians have done is they've simulated, they actually have population data, and they take samples, and they figure out, is that a reasonable approximation? It's actually not only reasonable, it's a little bit on the conservative side. It's probably going a little bit too far. You wouldn't have to subtract a full 1, but subtracting 1 is easy, as opposed to subtracting 0.793. So that's the reasoning behind kind of having a sample variance that's different from the population variance. All right, why don't we go over to this side? Over here, we said that we had means. Why don't we see if we can get some SDs, and the SDs come in two varieties also. There's the population SD, the standard deviation, but also there's the sample SD, which is what we're usually working with in a practical sense. Anybody want to remind us how we might be able to go from a variance to a standard deviation? You may have done this in Psych 2, and maybe you're not recalling it, or maybe you didn't do it in Psych 2. Yes. People are not sure how to get from one to the next. Some of us are not sure. Okay, then it's time for a mantra. That's what we need. We need a mantra. I'm going to put our mantra up here. And that is that the standard deviation, the SD, is the square root of the variance. You don't say that together, I'll say it once, and we say the standard deviation is the square root of variance. Everybody? The standard deviation is the square root of variance. That will always be true when you're dealing with the distribution of means and then moving back and forth between a sample and a population and the distribution of means. If you ever have a variance, and sometimes in different statistical settings, you'll be presented with a variance. If you want the standard deviation, you could simply take the square root of that variance and so if we wanted the population standard deviation, we would take the square root of the population variance. If we want the sample standard deviation, we would take the square root of the sample variance. Who's following? Let's see if we can do that. Okay. Does anybody happen to know the square root command inside of Excel? There's a couple of ways we can do that. Okay, very good. Victoria's got it. So we'll say equals because we always do that when we're telling Excel we want to command. SQRT is the abbreviation for square root. Okay. And we can take the square root of, I'll click on this guy, this is my population variance. And I come up with a 1.88. Okay, let's do that. Oh, you know what? I can do it one more time by putting an equal square root and clicking on this one, or because these spatial relationships are appropriate, I can just say, let's go down one and play the same ball game. Okay, so I'm going to grab on this knob, I'll drag down, and I wind up with that. So I wind up with this guy is equal to the square root of the neighbor who's up 2 or 3 floors and over 2 or 3 homes. Okay. How do you get 1.93? All right, let's do this. Let's do our little check. I'm going to put the word check down here. And many of us are sitting in the room know the actual command inside of ourselves to, in one shot, do all the steps that we just did manually. So, anybody want to yell out that command? If you know, I'll give you the first bit. It's equals. Think of the standard deviation. It's STDEV. Left to right. STDEV, and then we're going to go like this. So just like we did for average, we said equals average, and we highlighted over the range of scores for which we want the average, and then we put in the right paren. I'm going to put in my right paren here. I'll let you hit enter, and I'm deliberately not in there so you can see my syntax. Can people hit enter? And what'd you get? The same as this one. Let's see if that works. I'll hit that. Okay, real good. And so you can see that something like, I don't know, that's 10 degrees precision or whatever that is. We just went through the steps manually when Excel doesn't not put. It's easy to put in average, and I know that you know how to do it. You probably didn't know, or you might not have known how to do a standard deviation, but now hopefully you know. The idea of the standard deviation is we have a list of scores, figure out how they deviate from the mean, we square that. So now we're in this weird kind of loop that we've actually given additional weight to really strong outliers by squaring it. But it does get rid of the negatives. We sum those up, we divide by the number of scores in the case of the variance, or we have this approximation of n minus 1 for the sample. And then we need to go back from the squared units to to the unsquared units, back to the more original unit of measure for this depression score. So because we squared it, we can undo that by taking the square root. People see that intuitive? Because the variance is this stated as some kind of square root, which isn't all that helpful relative to the root. Maybe we have a different way that we might have taken the square root. Think about this. Does this really make sense? We did this and we raised it to the second power. Let me undo it. Okay, great. Over a half, right? So what you could do is you can say, I'll move this down here. This is equal to this guy, sample variance, okay, raised. How would I express that as a decimal? 0.5, raised to the 0.5 power. Okay, and that would result in the same. So we can take a given quantity, raise it to the 0.5 power, and that is the same. We're raising it to the 1/2 power. All right. So now we've done all questions so far. How many people learn about new Excel commands? Okay. How many people learn something about how the standard deviation actually works? Right. Good. So I can never really tell how much of this is being done for Site 200 because some of you have similar concepts that we are doing. Why don't we do this? The depression scores seem to be ranging. Well, why don't we use Excel to have the depression scores range and available to us? Why don't we say equals, and I'll give you a new command. This one is max. You might remember that I had a max command operating on that randomly generated set of numbers for the student equals max. And why don't we highlight over the 20 scores? And this will tell us, just like that, what our maximum score is. I got a 9. Did anybody else get a 9? Anybody have an idea about what the command might be if we wanted a minimum score? Okay, yeah, you can always give it a shot, right? You say, I wonder if Excel has a command like this. Equals min, and we need to make sure we go over the 20 scores. Okay, so it looks like we've got a range that expands from 2 to 9 with a mean of this and a standard deviation. One more we'll do. Suppose we wanted to get the standard error. How about that? We wanted to get the standard error. We have the standard deviation. We want to get the standard error. First, conceptually, let's not get complicated. Well, what is the conceptual difference between the standard deviation and the standard error? Something help us out with that. By conceptual, I mean, what does it mean in plain English? Without actually telling me about the computation. Standard deviation versus standard error.
The standard error is the standard deviation of the distribution of means.
Okay, thank you. So what we did here was the mean of this sample, pretend that's a sample, and then we did the standard deviation of that sample. But if I took another sample in the price matrix, also 20, and equals 20 the next time, I might get a different mean, but it would probably be pretty close to 500. It wouldn't be out as high as 900. It wouldn't be out as low as 2. It would be pretty close to that. Maybe it'd be 5.3. Then next one would be 5.7. Next one would be 5.6. We get a really tiny dispersion of means. We have a distribution of means. We can build a distribution of means. And then we can ask, what's the standard deviation of that thing? And that would be our standard error. So that's it conceptually. What number is that? Now, that was the conceptual question. Can somebody help us out with the computational bit? Now that we know what it is, how would you go about computing it? Maybe you probably yell it out. The standard error is equal to okay, excellent. Standard deviation divided by the square root of the sample size. So, why don't we, somewhere over here, and I can label these things. This guy was the max. This guy was the min. I'll call that one the double check. Okay. Why don't we put in now SE? And this will be equal to this sample standard deviation divided by the square root of, you tell me what n is going to be? And here is 20, right? And in this case, we actually do divide by the sample size and we divide by the sample size minus 1. We already did sample size minus 1 step when we computed the standard deviation. So let's see if I have a typo here or not, but I came up with 0.43. Okay? that's kind of interesting. Let me turn that red just for a moment so we can all see it. And I'm going to turn its conceptual counterpart, the SD, over here. Okay? So our sample standard deviation is 1.93. Look at the standard errors. A little smaller than that. And that's what we would expect, because we know that the population probably has a big distribution like that. Our samples can be fairly spread out, but the distribution means should be a lot tighter. And computation will be divided by the square root. Who's okay with all that? And one more time, you could have divided by the square root of n, or you could have divided by n raised to the what power? So that would be the equivalent of doing it. Okay. Questions so far? Just to show you that we've built into Excel an absolutely gorgeous set of spatial relationships. What I'd like to do now is muck around with this set of scores in the following way. We said that we had a high score of 9, and we said that we had a low score of 2. Who's okay with that? Okay? So why don't we play around, and why don't we say that we're going to simulate scores based on our sample. And one of the ways that we can do that is we can take advantage of yet another Excel command, equals rand between. So if you'll join me by going up to cell, which cell is that? That's cell C3. And why don't we simulate what we had? What was our minimum and maximum score? 2 and 9. So why don't we say, well, this can be any score between 2 and 9. That was equals, the word is rand, between 2 and 9. And hit enter, and I happen to get a 9, but if I hit the F9 key, that number is going to float around on me. What I love about this is that that number alone is enough to drive changes throughout this entire display. I'm going to move this over to here so you can see it all in one shot. Just grab that whole package. You want the F9 key. And all that's being driven by the change in the one score. You can see that we've got the mean hopping around, we've got the population variances and everything else hopping around. Right? And then why don't we do this? Why don't we make the entire range of scores randomly generated? So we're going to use the formula in cell C3, but we'll grab on that bottom right knob, we'll drag it down, and your scores will not look like mine, and your scores will not look like themselves after we hit the F9 key. What's cool about this is all of those numbers are correctly computed because we have the same spatial relationships. It's now properly novelly generated numbers, randomly generated numbers, occurring within the same range. Who's remember that? So pretty powerful. And in many ways, I think what's beautiful about Excel is you get to develop some of these solutions. It could have been that you had a handheld calculator. You push on a button, you get the standard deviation. In Excel, you can essentially push on a button, the STDEV command, and get out the standard deviation. You push on a button, get out the standard deviation. But this allows you to now see what is going on. What are my scores? Here are the deviates, here are the square deviates, here's some of the square deviates, here's the variance, and those are the different flavors of standard deviation. And all lays it out, I think, very well.
Is the standard deviation like using STDEV? It does the same.
Thank you. Yeah, I might not read that clear. That's a very important point. Excel made the assumption that you're always looking at a sample. Okay? So if you wanted the standard deviation for the population, it could be. Well, let's just take a peek. It might be that they've not created a command for that. Okay, right. So there are lots of different variations on this. And if we wanted to spend a lot of time on that, we could probably get some help and say, this one does a particular kind of deviation. But the one that it defaults to is standard deviation for the sample. And the way that you might verify that is you might see that these two have identical phenotypes, 2.33 on my screen, etc. But one is being created by the square root of the sample variance. The other one is the STD. And that was actually a good move on the part of the programmers at Excel. Because almost always in the real world, you will have samples. Almost never will you have access to the entire population. Okay, so that was, if they had to choose one, that was the much better practical choice to make. All right. Questions or comments? All right, why don't we go ahead and do some other kinds of things on our, either in Excel or in SPSS. Let's see. Okay, let's a couple of other things I wanted to do. Can you do what I just did? I want to make sure people are comfortable doing this. I grabbed this packet, I highlighted it, and then knocked down here, knocked down in that lower right corner, but somewhere in any one of the other sides, I grabbed it with my cursor and just slid it around. And you do that because we're going to do a little bit of target practice. There are going to be times when we get into more involved computations. In our Excel spreadsheets, we get a bit messy and we need to move things around. So we get a little bit of motor skill practice here. It would help if you can just slide that around while always leaving the information intact. You able to do that? There are other ways of doing this too. We can do something like this. If you highlight the entire region one more time, then you do Control with your left pinky, X with your left index finger, Control X, and you get a ring around the rosy. And so we're going to now cut this, and we'll paste it. I can put my cursor here, and then Control B is in victory, and it goes right there and control. So sometimes it's easier to drag and click, other times it's easier to Control X, Control V. And all the while it retains, it picks up all of those geotypes. So the spatial relationships remain. Just so we're all clear on this, let's highlight that one more time. Okay. Now instead of doing a Control X, let's do a Control C as in copy. Control C. First we'll see if we get that much. Okay. And how many people are getting the ring around the rosy? Okay. All right. And then go to some other open space, whatever works for you. And now do a Control V as in victory. Uh-oh. So when we did a Control X and Control V, the world was fine. Now all of a sudden, the world has become comfortable. What happened? Anybody tell us why that did it? They seem like we've made fairly similar motor responses. Control X, Control V works just fine. Control C, Control V didn't work so well. People are not sure about that. Okay. How many people think they have a guess as to why? Thank you. Okay, so some of the functions didn't calculate. Let's see if the functions calculate. Okay, so let's take a look over here. Look at this. The word SD copied. In fact, it looks like all of the regular text copied. But when we had to do a computation, somehow we got ourselves into trouble. Let's take a look at up here. My computation for the population SD is equal to the square root of F. That looking for us, the square root of F. Over here, we have the square root of F and Y. When you copy, you're actually copying one more time now the relative spatial positions. Okay? So from relative to this guy, he's at H. This cell is H16. Some people see that it's H16. And what he's doing is he's taking the square root of F24. So he's going over and down. Yeah. It's going over 2 and down, I'll call it 10. Up here, if we go over 2 and down 10, what happens? Okay. So we need to be very, very cognizant of what exactly is being cut. Is it a genotype? Okay. Which is the underlying formula? Is it the phenotype, the number that's being expressed? We need to be very, very aware of that. So I'm only pointing that out now because there is a difference between saying I want to make a Control C and a Control V, I want to copy something, versus I want to paste something. I'll go over here and I'll now do a Control X. I'll paste that over. And one more time, I'm still on F24, which is where I was in the moment ago. So I'm actually taking that value, and I'm just now repositioning where that's all being computed, but I'm staying on the same target cells.
So it is randomly generated.
Yeah, but that's only because we have the, it's not like the move that's generated the new. We're getting into it because we froze but we can these into and if that's bothering you, I will unrandomize these guys, and I'll say just for the moment, Control C, and I will now paste in those literal values. I have still the same 4.95 that I had a moment ago, but now I've got frozen values here instead of bringing in general values. Well, a little confusing, but what I want you to take home from that is that Control X isn't the same thing as Control C. Because sometimes you're picking up a spatial relationship, sometimes you're picking up something like a literal value. Okay. So we know how to move things around, we understand cutting and pasting and some of those differences. Okay. Why don't we do this? Why don't we have about 10 minutes and we haven't made any progress on SPSS. So I want to make a little progress maybe on SPSS. You can come back and do more things tomorrow in Excel. We have a few more tricks to learn. Why don't we do this? You'll join me out in SPSS. What I hope you will do is pop open SPSS, and then if you can go to the File, Open Data in SPSS, and we'll open up our old friend, the GSS 94. It has something like 1,500 pieces, more than 9 variables, or whatever it is. Pretty good sized data set. And just to remind you where that is, and there's a good chance that our quiz will have some questions on this one. We go out to the S drive as you're navigating through your data file. We go to our Site 370 class, the resources folder, the practice. Here's the GSS 93. So I'll leave that tab up there. When you get there from the raise your hand, you can see maybe you can help your neighbor get there from neighbors. Fumbling as I often do through these menus. Okay, how many people are there? I think that's 10 out of 10. Okay, why don't we do a few things, and many of these might be familiar to you. In fact, you might know some tricks in SPSS that I don't know. We can learn from each other, but there are a few things I would like you to know, and I'll presume for the moment that maybe you don't know them. What we'd like to do is sometimes take a look at the full data set, and we can toggle back and forth on the data set. Actually, it was Gabby who showed me a new trick yesterday, a new trick for me. If you're on the data view, you can click on this one and get either the values on the all the way up here. You can toggle between the value labels and these are numeric representations. What we sometimes would like to do is say that we have 1,500 people, but we want a particular subgroup group. Maybe, for example, we want only the men. We want only the women. So we have to somehow be able to identify subgroups, then describe them, and then maybe describe a different subgroup. So how many people have done that before in Excel? You're taking a big data file and you're giving just a subset based on some criteria. Done that. Many people are not sure we've done that. It's all pretty new. Okay, why don't we do this? Since it's kind of a fun variable, that age from first grade, and we took a look at that one last time around. People remember seeing that one, age from first grade. Why don't we subdivide that? And why don't we take a look at the same variable, but we'll look at the age from first grade for men, and then we'll look separately at the age for first wedding for women. And how do we go about doing that? Anybody have an idea? Looking at the many menus that we have. All right, why don't we go to data? Hopefully everybody's on data, and that's an incredibly busy menu. We go down to select cases. So of the 1,500, we're going to select some kind of a subset, and we'll see what the menu options are there. So just so you're all with me, that was data, and then select cases. You might make a note of some of these steps. And it always defaults to this. If we want to get a subset of data, we might go to data, select cases. It always defaults to all cases. Everybody's been figured out. That's the first thing, and that's just how it's normally set. And most of the time we want it that way. But other times we want to look at a particular case. A case, again, is a row in SPSS. I want to look at a particular case if a condition is satisfied. So can you join me by clicking on that? So the condition is satisfied. And then we'll go ahead and spell out this if statement by clicking on the if over here. And let me pause and see how many people got to this select cases if menu. Are we there? See if I lost any. Are we okay, Shelby? Okay. All right. And so why don't we go to the age when first menu? That's maybe the fourth one on the list, so you click down 3 times. And can you slide that over? So we're going to select this case. We're going to select a case based on the age when variable. And why don't we say if it's equal to, and by the way, I can show you in another scheme that the way they coded this is they've used a simple 1 and 2 for male and female. Where this one goes, I think they have 1 for male, 2 for female. So why don't we take a look at the men first. Age wed equals 1. If that's true, then we want the case. If it isn't true, then we want SPSS to momentarily hold the case thing and not make it part of our analysis. And can we say continue? And then we'll say OK. And we can minimize that screen there. And as you look down this way, hopefully you'll see that we have some cases that are in and some cases that are not. Let's make sure that we didn't get rid of everybody. Oh, I'm sorry. Try that again. My bad. Let's go back. And you might make a mistake too during an SPSS quiz, and you'll have to go back and correct it. Let's go one more time to data. Select cases. I put in the wrong variable. Let's go back to here. Here's what I really wanted to. I'm interested in age wed, but I'm actually interested in the sex variable. Okay. Because you wouldn't get married at age 1. Yeah, right? That would be really early. Let's go back. Let's throw out age wed. And the sex variable, I think, is maybe, let's see, I think it's the 14th one down, so you click down 13 times. 2, 3, 4, 5, 6, 7, 8, 9, 10. Respondent sex. That's what I should have done. And I'll point there. You can slide that one in. If that's okay, then we've got all the people see that, you slide that over. If the sex is equal to 1, that means they're now you say continue, now you say okay. And that makes a little more sense. Now as we're looking at the data sets, you'll see that roughly half of them are crossed out, roughly half of them are in, roughly half of them are in. So now the only live cases in this thing are going to be the men. Who's following that? So now that we have men in there, why don't we do something that we've done once before, just to get a little bit of a loop. Why don't we generate some descriptive statistics on the age wed variable, what we were shooting for. So let's go to Analyze, Descriptives, and why don't we go to Frequencies, because we're talking about frequency distributions. We get a frequency distribution on the age when first wed variable. And that was Analyze, Descriptive, Frequencies, age when first wed. And you might remember we did something like this. We went to charts, and we'll take a histogram, we'll envelop it in that big Gaussian distribution, even though the actual data might not be Gaussian distributed. We can also look at some statistics, so that's okay. And why don't we take all the dispersion measures, because we like those. We can take a look at skewness and kurtosis. We can take a look at all the simple tendencies. You might remember that they call the sum of mass. We have this little thing to do that. We talked earlier about quartiles, the 25th and 75th quartiles and so forth. All right, why don't we say continue? Why don't we say OK? And then we should now get something like 492 cases. We can see that the mean is 24 years for these men. I'll make that bigger so you can all see it. And that's how the distribution looks. And we can go down that top and see what the skew is. But now we have age wed just for the men. Just follow me. And just to remind you, if you were to go over to data view and you went to the 14th variable, you could look at the values here for respondent sex, and that's how they kind of put the bonus down to the screen. We have just a minute left. I wonder if we can do this. Can we now do the same thing with just a couple of clicks, and we'll now get the same distribution for the females. So let's click out of that, and we'll go to data, select cases. We still want to select on this sex variable, but we want to change the 1 to a 2. That was data, select cases. We'll still stay there, 1, 2, we'll say continue, we'll say okay. And then maybe one more time, we'll go to analyze descriptives and frequencies, and we'll just leave all that the same. And now we get exactly the same information for the women, and they have a mean of 21 for age of first marriage, and then here we have 24 average for the men, 21-ish average for the women. People follow me. And you can select based on any number of cases. Okay, we're at that time, and I like to start on time, I like to end on time. This is a very good session. When we come back tomorrow, we'll take a look at your 10 questions. We'll do that maybe half the way through. We'll do a little bit more poking around in SPSS and Excel, so we're well prepared for Thursday's. Thanks for a great session. Hope you enjoy the rest of your day. See you tomorrow at 8:30. Back to our usual time.